Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, Senior 4 chemistry students. Welcome back. I'm Alan and happy to still be with you in chemistry lessons. I hope you're fine. We are still continuing with the topic of periodic table and heading into lesson 4 of our unit 14, which is about period 3 elements and their compounds. So we are going to be looking at the chlorides of period 3 elements and in our today's interaction. Please, if we're having any new member who is joining us and did not attend the previous lesson, I'm going to do a quick revisit on what we looked at for you to catch up so as we can move on together. So in the previous lesson, we looked at the preparation of period 3 oxides and their melting points together with much of the other physical properties. So, in terms of preparation, they are prepared by direct combination of that element of period 3 with oxygen. That is from sodium to chlorine. Remember, argon does not combine with other elements. So, as you can see on the slide, when you combine these elements with oxygen, they form their oxides. And these are the formulae for the oxides formed. And we can directly look at their melting point as we do a review. This is basically for that student who is just joining us today and did not take part in the last lesson. I'm bringing you to almost to a closer contact with what the other students looked at. So in terms of the melting point, when you're explaining trends in the melting point, you can't miss these two terms, the giant lattice and the simple covalent molecular structure. As you can see, from sodium to aluminum, they exist as giant ionic lattice. These are the oxides. Silicon dioxide is a bit unique. It is existing as a giant covalent lattice with very, very many silicon and oxygen atoms together. As you can see in the structure, this indicates that there is a bond connected to other more silicon, a bond connected to other more silicon atom, and so on, bringing about this silicon dioxide to be a macromolecule. If I can bring it to simple understanding, silicon dioxide is the usual sand. You know this sand that you normally pass through as you go to other normal or usual activities. The sand is basically the silicon dioxide. So when we leave that, we looked at these other oxides from phosphorus to chlorine, which exist as simple covalent molecules. Of course, the forces of attraction is dispersion forces, which is weaker compared to these giant structures. And it is only dependent on the molecular sizes. So a molecule with higher molecular size then will exert a stronger dispersion forces, bringing about higher melting point. As you see, for example, the oxide of phosphorus, if you compare it with the oxides of sulfur and even chlorine. So it has a higher melting point because of it's a bigger molecule with a more number of electrons, bringing about stronger dispersion forces. So that is what we looked at. Then we looked at their reaction with water. If I can quickly also bring you to touch, we said they move from strongly alkaline, that is for sodium oxide, to strongly acidic, that is for the oxides of sulfur. As you can see, the pH when you dissolve them in water. These two they are insoluble, that is aluminum oxide and silicon dioxide. They are insoluble in water, but they still have the amphoteric nature, that is for aluminium oxide, and silicon dioxide has some acidic properties. It only reacts with strong bases, and that is mainly sodium hydroxide or potassium hydroxide. So that is what we looked at in the last lesson. I hope you have an idea on what we looked at. I would implore you to go ahead and look for that content so as you do not miss a lot. Let's now head to our lesson, which is the period 3 chloride. It's lesson 4, please take note on that. So what we are going to look at is, we're going to be looking at the preparation and the type of bonding that exists in those chlorides. Then we also look at the overview of the uses in our day-to-day lives. And the key terms that we're going to focus on mainly are what type of bonding. Is it ionic or covalent? And if it is covalent, what would be the reason behind it being covalent? And that is where we shall be seeing the polarizing power or the polarizing effect of different cations bringing about covalent bonding. Then we look at one other crucial term which we call chlorinating agent. Chlorinating agent is that substance which adds chlorine to another. We're going to be seeing it. Since we are looking at the chlorides, we expect to be meeting much of the chlorinating agents. And the lesson objectives, which I always end up when I'm doing the introductory part, is we are to explain how the chlorides of basically sodium, aluminium, magnesium, and phosphorus are prepared. Then we recognize the uses of those chlorides in our day-to-day life activities. That is what we are going to basically look at. Let's get started on the preparation of the period 3 chlorides. So, as you will come to notice, like the oxides, even chlorides of period 3 are prepared by direct combination of the atoms of the elements with chlorine or with the compounds of chlorine, like as we shall see with the silicon. So we are going to use 5 elements to generalize the whole of the preparation, and that is sodium, magnesium, aluminium, silicon, and phosphorus. Let's get started with sodium chloride. That is the chloride of sodium. Let's have a look at the slide. We all take common salt, don't we? And most of you already know it is sodium chloride. Yes, that is the common salt you take, which is normally called table salt. That is the table salt. You see the illustration on the slide? That is the common table salt that you normally add in food when the food is not having enough of the salt. It is indeed sodium chloride, made up of sodium and chlorine. It has a few uses, as we said. We shall also be looking at the uses. Before we look at the preparation, let's quickly look at the uses. It is for food seasoning. Of course, you can witness, apart from people with high blood pressure or with heart diseases and so on, most of us enjoy salt. We enjoy feeling that salt content in our mouth as we eat. So food without salt, in most cases, it is not tasting well. Some of the uses of sodium chloride is for food seasoning, and it alleviates dehydration. That is for both for the children or the kids who are diureting, and even to the old people. If they are not taking a lot of water, then they are susceptible to undergo dehydration. If you go in the hospital, they will give you sodium chloride solution. So you see how it is useful. Well, after understanding that we are having sodium chloride in our day-to-day life, how is it exactly prepared? Majority of us have grown up in areas where sodium chloride is normally harvested from salty water, like in Lake Katwe in Uganda, and I think around other more places, they harvest sodium chloride because it is existing naturally. But in lab, we also produce it. And how is it produced? Again, the point is combining the element with chlorine. So you get sodium, heat it with chlorine gas, then you'll get your sodium chloride. In the process, there is light and the heat that is produced. Take a quick look at the experimentation in the lab within our conical flasks. The first conical flask, as you see on the slide, is indicating the mixing of chlorine gas and sodium metal. As you burn the two, there is this bright yellow frame that is produced, even producing sodium chloride salt. You see that bright yellow frame with the sodium chloride produced, which crystallizes to get our sodium chloride crystal. So the point in here is to see the light that is produced and even heat that is released. And as usual, as we talked of, we have to include in the bonding, it is having ionic bonding and exhibits giant ionic lattice structure. Where is the ionic bonding comes in? From your ordinary chemistry, ionic bonding, one atom loses, another gains. Chlorine having a higher electronegativity value, so it gains an electron from sodium, leaving sodium with a positive one, and chlorine gains a -1. So there is attraction between the positively charged ion and the negatively charged ion. That's why we call it the ionic bonding in that common salt, sodium chloride. So that is sodium chloride. I think we are very much conversed with sodium chloride. We are staying with it, so we don't need to take much more time on that. Let's go to one more crucial component, and that is magnesium chloride. That is the chloride of magnesium metal. Like we looked at the magnesium oxide, whereby it is produced by burning magnesium with oxygen. Similarly, to form magnesium chloride in the lab, get magnesium ribbon, burn it with chlorine, and it forms the white salt. Look at the white salt, which is magnesium chloride. It is also in crystals like sodium chloride. I may pause a little bit. What do you think is the type of bonding that exists in magnesium chloride? I ask, what is the type of bonding that exists in magnesium chloride, referring to sodium chloride? Yes, as you would imagine, it is also ionic bonding with giant ionic lattice. And where does it come from? Magnesium losing two electrons, one electron taken by chlorine and another electron taken by chlorine to form magnesium 2+ and two ions of chlorine or anions of chlorine. And so the 2+ will be in attraction with the minus on chlorine, forming the ionic bonding. So you're seeing from +1 of sodium to +2 of magnesium. We're also going to look at +3 of aluminum, and so on. Similarly, even this magnesium chloride is useful, surprisingly. It is useful for body relaxation. It is actually formulated in most of this shampoo, body shampoo, and so on. So when you apply that lotion on your body and you feel, oh, you're feeling that relaxation, part of it is having this magnesium chloride. In addition, we know our body requires magnesium for functioning of cells. So if you consume magnesium chloride, then you're bringing in the magnesium ions in the body. But what is very, very crucial in here is its calming and relaxing tendencies. And as such, it's normally used for bathing and making the body shampoo. Hope we are moving well. You see, these salts, let the chemical term not confuse you and say, oh my God, what is this? No, these are the usual materials that we always interact with in the normal life. Let's quickly look at aluminum chloride. This is a quick review. We looked at aluminum chloride when we were looking at the chlorides of aluminum in period 3 elements, but let's quickly look at that. Simply burn aluminum with dry chlorine and you get anhydrous aluminum chloride. Anhydrous meaning it lacks water of crystallization. These two illustrations show you when we talk of hydrated and anhydrous. Hydrated has some water molecules. So if these are crystals, because they're having some water of crystallization. This is just anhydrous. It is a bit dry. It does not have the water in it. So if you were aiming at forming anhydrous, you need to use dry chlorine. If you use any chlorine gas with some water, then it's going to distort your product. Briefly, this aluminum chloride is used in chemical analysis, unlike the other two, sodium chloride and magnesium, which are commonly used in our day-to-day body contact. But this is mostly used in chemical analysis. Another question I pose, what type of bonding does exist in aluminum chloride? I need you to take a guess. And if you already know that, share it with a friend. What type of bonding does exist in aluminum chloride? The nature of bonding is basically covalent bonding. Is predominantly, this is a crucial word, predominantly covalent bonding. Let's quickly see how it comes about. It may be confusing. Aluminum is a metal, chlorine is a non-metal. How come it is forming covalent bonding? This is covalent bonding in aluminum 3 chloride. How does it come about? We all know, let's focus over here. We all know that aluminum is a metal. And being a metal, metals lose electrons to form cations. So it will lose all the outermost electrons, the 3 electrons. It is in group 3. So we expect chlorine as a gas. Why I'm dividing, chlorine exists with 2 atoms combined together like this. So I'm dividing to take 1 atom. So a half of chlorine molecule brings me 1 atom of chlorine. Will gain 1 electron to fill up its outermost shell, and so it forms chlorine minus. If I can use the dot to indicate 1 electron and the X to indicate another electron, the dot for 1 electron, it has gained this electron in here. It is being gained. So if we have to balance this, you will end up having, remember the electrons lost must be equal to the electrons gained. So we need to multiply by 3. You'll end up having aluminum as a single atom will lose 3 electrons to chlorine to form aluminum 3 plus with our 3 chloride minus. Now, this is where the covalent nature comes in. From your ordinary level, you understand aluminum being plus, it is now going to be surrounded by chlorine, and chlorine. Again, using the dot to imply the electron that it has gained, and the X to be the electron that the chlorine is already having. So I put this to be the electron density of chlorine. A minus implying chlorine has gained an electron. So due to high polarizing power of aluminum, it tends to attract this electron density towards this highly charged cation. So the electron density is tended to be attracted by the aluminium 3+, meaning that these electrons that are making up, that are onto the chlorine, will be pulled towards aluminium. The end product is the electrons are not completely onto chlorine, but they are between aluminium and chlorine, and this brings us the sharing nature, which is unique for covalent. So in this way, we shall have the electrons in between chlorine and aluminium, chlorine and aluminium, and chlorine and aluminium. So this is where you have the predominantly covalent bonding. It had the ionic part by losing, but because of high polarizing power brings in the covalent nature in aluminium chloride. That's very, very, very crucial with this part. And it brings up to these unique characteristics. What are those characteristics? In solid form, aluminium chloride exists as ionic lattice. It still has these ions because electrons were not completely shared from one and here, but they were pulled and appear to be shared. So in solid form, it exists as ionic lattice. Then in gaseous form, it exists with the covalent bonding as a molecule. Point second. Now let's look at silicon tetrachloride. It's a liquid, but very, very volatile, also formed on a commercial scale by heating silicon with hydrogen chloride. This is essential liquid, as we are going to see, so it is even produced in industries. The type of bonding, it is simple covalent, as you'd imagine, in silicon having both metallic and non-metallic properties, and chlorine being a non-metal, so they form covalent bond. And the electrons are shared between silicon and chlorine. Quickly, let's look at the uses. Most of you, when you're buying the water bottles for using at school, inside that water bottle you've bought, even from like Tido Mill or 2000 supermarket, there is normally a pack of silk gel. There is normally that pack of silk gel. Try to notice, or in the bags that you normally buy, there is normally that pack of silk gel. It is just produced from silicon tetrachloride. And its purpose is to act as an absorbent material or a desiccant. It removes the moisture to prevent microbial contamination within the bags or bottles. So how it is produced, it comes from the silicon tetrachloride. It's a crucial component. And let's now look at the last part, which is the chlorides of phosphorus. There are two categories. We have phosphorus trichloride or phosphorus 3 chloride and phosphorus 5 chloride. This implies phosphorus is using 3 electrons in the outermost shell. Here it is using all the 5 electrons in the outermost shell. This is a liquid and this is a solid. You see this is the pale yellow phosphorus pentachloride, or we can call it phosphorus 5 chloride. These are the structures. Remember, phosphorus is in group 5, it has 5 electrons. 1 electron here, another electron here, and another electron here. The remaining 2 are the ones indicated in phosphorus trichloride. So when it is forming phosphorus pentachloride, the 2 chlorine atoms added on phosphorus trichloride take up 1 electron here and another to create these bonds. So that is how they are formed. You notice the conditions involved. Let's quickly look at phosphorus pentachloride, you see the formula I've written, P2Cl10. This is not a mistake. That is actually how phosphorus pentachloride exists in the solid form, this pale yellow. That is how it exists. And let's look at that abnormal behavior. Basically, phosphorus pentachloride has that abnormal behavior. In solid form, it exists as ionic salt. Phosphorus combined with 4, let me illustrate it from here, 4 chlorine atoms, but it will have lost 1 electron, then this has 6. These come by joining 2 phosphorus pentachloride molecules. You see this is 5 chlorine atoms. So when 1 is lost to another fluorine, this chlorine lost to another fluorine, then it remains with 4, but it will have lost an electron. That is why it has this negative. It comes from chlorine coming with another electron. Then this will have lost, and so it possesses a positive. This attraction of the positive and minus brings in the ionic bonding. And this is why it exists as P2Cl10, divided in as PCl4 positive and PCl6 negative. It's a unique behavior for PCl5 or phosphorus pentachloride. And this unique behavior affects even the melting point, as we're going to see when we come to the properties of the chlorides. That is why I needed to bring in, and as I conclude, they are also useful. PCl5 and PCl3, they are useful. One as chlorinating agents. They add chlorine to a substance, and they are used to make batteries, like the mobile phone batteries. You see this LG battery. And they are also used to make antibiotics, that is for PCl5, and even to make insecticides, that is for PCl3. So that is it. We can quickly have a summary of what we've looked at. And the summary, you see it, method of preparation and the different properties. Please, thank you for participating in this lesson. Stay safe. I would wish to meet you in the next lesson. Bye.